Okay, now it's a common misconception that from Hubble's results that if we look at our galaxy, so this here is the Milky Way, and we have a few other galaxies around us, lots of different shapes of galaxies, and we'll put another few over here, another one here, another one here, that if these are all moving away from us, we kind of must be at the center of the universe, and we might kind of take it bad that everyone seems to be trying to get away from us, but that's not actually the right way of looking at it, because in the future then all these galaxies will move away from us, and the ones that are further away will move faster, and what we end up with is it doesn't really matter what galaxy you were in, all these galaxies would observe that in the future all the galaxies are further apart from each other. So if we are here and we look at all the galaxies, they all appear to be moving away from us. However, for some little alien in this galaxy, from their perspective, all the galaxies would also be moving away from each other. A good analogy of it is, I don't have a balloon, so I can't demo this, but if you have a balloon and you kind of draw the galaxies on them, and you then imagine that balloon being inflated, what you would see is all those galaxies get further away from each other, and it doesn't matter which galaxy you kind of think of yourself as being at, they all get further from each other. So every single galaxy will observe the same thing. So therefore, we kind of say it's wrong to think of this as being a classical Doppler effect. Your syllabus very specifically mentions this, so I would learn off this sentence here. We should not consider the redshift of light from distant galaxies to be caused by their movement as such, but more due to a cosmological Doppler effect, which is more due to the expansion of space itself than any sort of movement. It's just another way of looking at it, but I would learn off that little statement. So Hubble published his results. He published his graph, which just say that, very simply, if the galaxies that are further away are moving faster away from us, and we get a straight line graph. Other people then came up with a theory to explain why this is, or the kind of implications of this. And what it kind of states is, if galaxies are moving away from us in the future, all the galaxies are going to be further apart from each other. But if we then rewind time, those galaxies get closer and closer and closer together, and at some point in the past, about 13 to 14 billion years ago, they would have been in a single point called a singularity, and basically all the mass and the energy that now makes up our whole galaxy would have been concentrated in that tiny point, and everything sprung forth from that in a massive inflation of space itself. That just produced everything we see in our universe today. Now that means that if you have more energy concentrated in a smaller space, the universe would be much smaller and also much warmer back then. And as the universe expands, it then cools down, and that allows certain things to happen. For instance, quarks to form together to form neutrons and protons. Eventually then, as they cool, the neutrons and protons move slower. They can form together then to form nuclei. Eventually, over time, there's less energy, it's less hot, the electrons move slow enough that they can be captured by atoms to form atoms, and then eventually the atoms move slowly enough that gravity can pull them together and eventually form stars and everything else. You can read through this paragraph that kind of explains this, but we do look more at the maths of this, which is, if we look at the graph, okay, and from our viewpoint, a certain galaxy is a certain distance away from us and traveling at a particular velocity. Now, that means that just using kind of speed equals distance divided by time, if this galaxy, say this is our galaxy, and if it's a certain distance away from us and moving at a certain velocity v, therefore if we rewind this in time, it would be traveling at a certain speed, s or v, okay, just equivalent to the v, but we'll use s because we're using speed here. Which just means we could do a very simple calculation if we know this value. Let's just call it v1, and let's just call this distance d1. The time taken is just the distance divided by the speed for it to be on top of us. Okay, for those two things to be together. And what we can find out if we put in our values from that graph, that would just be the d1 divided by the v1. And we can get a time where those two galaxies in the past would have been one. Now, we can then do that for a different galaxy that's further away. Okay, so our second galaxy, let's say that's the data for it, where this is d2 and this is v2, and let's say it is twice as far away. Okay, so the distance to our second galaxy is twice as much. But because this is direct proportionality, that means the recessional velocity will also be twice as big as it was before, and therefore if we rewind time, we would see it moving with a speed that's twice as big. So what that actually means is our first galaxy was a particular distance away, traveling at a particular speed, takes a particular time if we rewind time to get back. Our second galaxy that's twice as far away is traveling twice as fast, and therefore will take the same amount of time as the first case to be on the same spot. And it doesn't matter which galaxy we pick. If we rewind time, because of this direct proportionality, pick this galaxy, we'll take the same amount of time as the first one. Go to a galaxy that's 3 times as far away as the first one, got 3 times the distance to cover, but because of direct proportionality, we'll be traveling 3 times the speed. So they will all kind of, if we rewind time, be in the one point at the one time. Now, that time is just distance for red off the graph divided by the velocity off the graph. And it's very simple. It's a straight line graph. It's a very simple calculation to do. But that calculation actually gives you how old our universe is. Now, we can make things simpler because the gradient of that graph is equal to rise, the velocity, divided by the distance. So you should be able to see the time is just 1 over h naught. Okay, it's the reciprocal of this because we need a distance divided by a velocity. So if we do 1 over the gradient, which is just 1 over Hubble's constant or parameter, and that gives you the age of our universe. Okay, try these questions based upon that, and then I'll post a little video with the solutions below.